labs. Oh, if you haven't done that yet, it's time. Make that your next stop after this. Maybe 30 minutes after lunch? A little bit after. That'll be so fun. Well, like I said, we love our Lunch and Learn series. That's what that's what you're here for today. We want to thank our sponsors, Courtyard by Marriott here in Cartersville. They're really good partners for us, and we love the fact that they bring this to us. If you're a Lunch and Learn fan, next month, our Lunch and Learn is about coral reef conservation. We have Professor Dr. James Porter from the University of Georgia who's going to be joining us to talk all about coral reefs. He is a coral reef expert. He has helped restore our coral reefs here off the coast of Georgia at Gray's Reef, and he's going to talk about how that works. There may be MARTA trains involved. You should definitely come back and check that out if that's something interesting for you. This Saturday is our Spooky Science Saturday. Who wants to come back in their costume and go look for some aliens this Saturday? It's going to be really fun. It's going to be so cool. Also, if you are a scout or involved in scouting at all, you may not know we're having an event on November 8th. I was trying to say 8 and November at the same time. It did not work out. On November 8th, our first time doing an event called Scout-tacular. So any level of scouting, any scout you are, we've got something you could come do. You register your scouts for it so that they get a wristband to participate in the activities. But we're going to have the whole museum decked out with scouting activities, all kinds of different things you can do no matter what kind of scout you are. So please come back and hang out with us for that. It's going to be awesome. I have a quick question. We're trying to get a gauge on this. Can you guys raise your hand if you are here today because you heard about this event from our member newsletter or other member communications? Okay, that's a decent number. How about other general museum communications? You saw something else? Okay, just a couple. How about you found out about it when you got here today? Okay, all right, cool. Thank you guys, that's helpful. Well, I am so excited to introduce you guys to our Lunch and Learn speakers today. They are both on our education administrative team, and they want to help you learn more about space. You guys give a big welcome to Wendy Hayes and Carissa Zdanke.
Well, thank you, Hannah. Can you guys all hear me? Am I on? Are you on?
I think so. Am I on?
Yep. Okay, we're all on. Well, as Hannah said, my name is Wendy Hayes. I am the Public Programs Manager here. I am also a member of the SAS Squad. If you're not familiar with the SAS Squad, it's the super awesome science squad, and we come up and we love to do science demonstrations. And because this is all about JTS and Journey to Space, I have invited our astronomer, Carissa Zdanke, to help us with all of this. So, without further ado, Carissa, will you start us off?
I will take it away. So, welcome. Like we've been saying, we are so excited to be here, so excited that all of you guys are here today. We are going to talk all about a journey to space and what it takes to get astronauts up into space and what challenges that scientists and engineers have to solve to get them up there. But first up, let's start with Earth. What do we need to live on Earth? Oh, and by the way, this is going to be a really interactive Lunch and Learn. So for the most part, if we ask a question,
shout it
out, all right? So go ahead, shout it out loud. What do we need to live on Earth? Food, yes.
Oxygen.
Water, oxygen, all of that. Those are really good answers. But it's really hard to get that in space. Oh, yes, magnetic field. That's a good one. So for the most part, it's really hard to get all that in space. So that is one of the things that those scientists have to solve, how to recreate that so that astronauts can safely live up there. But first up, the first problem that we have to solve is energy, because we have to somehow come up with this energy to get a spacecraft all the way up into outer space. So they need a lot of force. And that goes into our first experiment. So we actually need a volunteer. Can you raise your hand if you'd like to be our volunteer? How about you at that table over there? If you can come on over
up
here. So we are going to have a balloon rocket.
So you're going to hold this. No, just hold it. And then you're going to walk to the edge of the steps.
Right over here.
Over there.
And you're going to pull it tight so that this is up in the air, okay? Alrighty, that's perfect. Awesome. So, our first rocket, you can pull it.
Yeah.
Nice.
And hold it up high. There you go.
Perfect. This is our first rocket of the day. As you can see, it is a balloon taped to a straw. But when we release this clip on the end, what do you guys think is going to happen to it? Exactly. So the air is going to come out of this side. It's going to go whoosh, and then the balloon's going to go whoosh, all the way over. That's what we think is going to happen, right? So this is due to Newton's third law, which states that for every action, there is an equal and opposite reaction. So we think when we release this, the air will come out. The equal and opposite reaction will be the balloon flying to the other side. Now, volunteer right over here. Would you like to do the honors? Do you think you can let go of this? Here, I'll switch with you. Hold on. All right. Go ahead and just release
We need a
that.
countdown.
Oh, yes, in on blast off, okay? 3, 2, 1,
one.
blast off! Take it all the way off. Oh, no, it's stuck together. Oh, I hear it. There it goes. Good job. Big round of applause for a volunteer. Thank you. You can head back to your seat.
All right, so just like a balloon, rockets also use Newton's third law. But in difference, rockets need fuel. So we want to talk today, we're going to have a few demonstrations on how we can create or recreate the thrust that forces our rockets up into space. So the first one that we're going to do is we have some liquid nitrogen. Now everybody take a deep breath in. And breathe out. You just breathed in 78% nitrogen as a gas. Now, we have some folks down the street, they're partners of ours, called Messer, and they're able to take that that nitrogen gas, remove all the heat energy out of it, and change it into a liquid. Would you like to see it? Yes. Okay. No, you don't want to see it? Okay. Okay. So I have it in here, and this is very cold. It is negative 321 degrees. So I have to make sure I have my safety equipment on, and
I've got
I'm going to go
mine too.
ahead. All right, so I have, a lot of it has gone out. All right, so I've got some liquid nitrogen in here. We're going to add it to our flask. And as we do, you can see that liquid nitrogen is evaporating, so it's going back into its gas form. And that's what we're going to use as a propellant to lift our rocket into space. Are we ready? So let's give a countdown. 3, 2, 1. And we're able to lift our rocket off.
That was pretty good.
Yeah, so it wasn't as awesome as NASA's rockets, but that's because they use something a little bit different. So I kind of have a recreation of that, a demonstration that I'd like to do. But for our demonstration, we're going to use alcohol and oxygen. NASA's rockets actually use a combination of liquid hydrogen and liquid oxygen. And when they combine those together, it makes a chemical reaction that creates that thrust that we see for the rockets. So inside of my rocket, I have some alcohol. So I don't want all this alcohol. I'm going to pour that out. Now, the next thing I have to add is what? Oxygen. Some oxygen, right. So thankfully, there's enough oxygen right here. You guys didn't breathe it all in when you asked you to breathe in. So we're going to hope that it all gets caught up into our bottle. So now, inside my rocket, I have a combination of alcohol and oxygen. All we have to do is light that up. So, Miss Krista, will you help me with this?
Of course I can. And again, we are using protection for this one. So when we say light it up, we mean it?
Yes. So we need our countdown. Again, we're going to simulate that thrust by a chemical reaction of fire with our oxygen and alcohol.
In 3, 2, 1.
That worked pretty well, didn't it? Yeah, that was the best one ever.
We practiced that one, and that was the best one yet.
That was the best one ever. So, I know you enjoyed rockets being launched off. I still have some, but I'm going to save them to the very end. But now we're in space. What happens next?
Well, space is a vacuum. And what a vacuum means is that there are little to no gas molecules. So here we have a lone gas molecule floating around in space, but he's going to come across planet Earth. And so planets like Earth, their gravity is strong enough to pull in those lone gas molecules, which means they're not out there in space. So here he's joining his friends in Earth's atmosphere. And those gas molecules are also creating air pressure. So that air pressure is pushing down on us at all times. But we're used to it. We don't really feel it. But in space, that air pressure isn't there. So speaking of a vacuum, here we have our own vacuum where we can try to recreate a little bit the vacuum of space. So first up, let's see, I'm going to scoot this up a little bit so everyone can see. We've got a regular balloon. Now we're going to put it in here, and when we turn on the vacuum, it's going to suck out the air from inside of this chamber. But there's still gas molecules inside the balloon. So go ahead and shout it out. What do you think is going to happen to this balloon?
What do you think is going to happen?
When we turn it on?
It's going to, what? Deflate.
Oh,
I've got deflate. Get big. Oh,
No,
I heard
pop.
lots of popping. Explode.
Explode, expand.
All
All right.
right.
Well, let's find out. Are we ready to turn this vacuum on?
Here we go. Keep your eyes in the vacuum.
You can see it is indeed getting bigger. It is expanding. So, like I said, we're taking out the air from inside of the chamber, so the gas molecules on the inside of the balloon are expanding to try and fill up that space.
Ooh, you may want to turn it off now. I don't want to pop. You want it to pop. I don't want it to
I know,
pop.
some people want it to pop. But
We don't want any popping going on here.
when we put the air back in, what do you guys think is going to happen now? Shrink? Back to
Normal
shrink, back to
size.
normal size.
I
It's gonna
still have some
pop,
popping.
deflate.
Yeah?
All right, let's find
That's it.
out. It went back to its normal size. So let's go ahead and take it out of here. It is a little warm just because the plastic stretched and went back, but no, it's the same size. Because this balloon didn't pop, none of those air molecules were actually lost, which means when it has that same amount of air pressure on it again, it can go back to the same size. Is it still going?
Nope.
No?
Did you hit it?
No? I didn't touch it.
Ah.
Hold
So
on.
Chris is going to have to really shout now.
How about now? There it goes.
Oh, there
okay.
she goes.
All right, next up with our vacuum, we have 2 marshmallows. I know. We're going to call them Scott and Mark. So we're putting Scotty here inside of our chamber. Now, what do we think? Again, remember what happened to the balloon. What do you guys think is going to happen to Scott the marshmallow when we turn this vacuum on?
What do you think? All the way in the back. Shout it out.
Puff up. Puff up, inflate, expand, shrink. Oh, these are really good guesses, you guys.
All right.
All right, well, let's find out. Are we ready?
Pay careful attention, whether you're watching on this screen or directly into our vacuum. Pay
Here,
attention
wait.
to what happens.
Let's put him in the camera. There you go. All right. Scott the marshmallow is getting bigger, right? So, yes, this jumbo marshmallow is increasing in size. It's because of the same reason as the balloon, okay? So we're taking out that air. There's a lot of bubbles on the inside of a marshmallow, so the air trapped inside of it, the air trapped inside of the marshmallow is expanding. But how big do we think he's gonna get? Pretty big, right?
He can still keep going.
Oh, I think he stopped getting bigger.
All
He's
right.
not getting any bigger.
So
All
what do you
right.
think is going to happen when we remove the vacuum?
He's going to go back to his normal
Back to the normal size.
Normal size.
Shrink. Anyone else? If you're in the back, shout really, really loud, okay? A wrinkled old man.
All right.
All right. You guys ready to find out? Poor Scott. He has become a marshmallow raisin. They're very different in size, though, right? That's because all those air bubbles popped, but so the original structure of the marshmallow just isn't there anymore. It can't support it. So it does collapse in on itself. Now, what we're going to do is you guys are going to get to make your own vacuum chambers.
Yeah. See, we don't want Carissa to have all the fun, right? And that is her favorite one. So we're going to be able to recreate our own vacuum chambers. And in just a second, you're going to be given a marshmallow and a syringe. Go ahead and hand those out. So if I can have my people helping out. So we're going to be going around. We're going to give everybody a marshmallow, or it's just going to be on your table. We'll leave it there. And when you get your syringe, this is very important information. It comes with a cap or a lid. So once you get your syringe, if some of our educators could come help out with us, that'd be perfect. So once you get your syringe, you're going to go ahead and take off the cap and just set it aside because we are still going to need it. So don't lose it. Again, this is for our junior scientists. We're going to give them all out to our junior scientists. You're going to take off the lid. The next thing you're going to do is carefully remove the plunger from the syringe. So now you will have two parts. Thanks. Anybody at the tables? Awesome. All right, so that's all you're going to do is take out your syringe and your cap. Don't worry, I'm going to wait. I won't going to go any further until everybody has their syringe in two parts. Their cap is on the table, and you have one marshmallow. Please don't eat your marshmallows. They've been open for a while. So, does everybody have one? Anybody is missing any of their pieces of equipment or materials? Oh, so a back table, our junior scientists. We have our back table back here. If you haven't received your 3 items, go ahead and raise your hand so we know where to come and get you. Again, we're doing it for our junior scientists. Make sure that we have enough for everyone. What are you missing? Oh, okay. So anybody else still missing anything?
There's extra syringes.
Huh?
There's extra syringes.
All right, so if you are
Actually, here's any
a senior scientist that wants to try it out, we do have some extras. I want to make sure that all of our junior scientists get our syringe and a marshmallow.
If you are a junior scientist that does not have a syringe and a marshmallow, raise your hand so we can find you.
All right, looks like everybody's good. All right, so the next thing we're going to do is you're going to take your marshmallow and put it inside your syringe. It should fit in there nicely. Then you're going to take your plunger and put it back into your syringe. And you want to set it to where it just touches the marshmallow. You don't want to squeeze it in there. You want it so it just touches the marshmallow. Yep. Just touches the marshmallow. All right, are we ready for the next step? Very easy. You're going to take your cap. Remember I told you to keep this safe. You're going to put it back on top of your syringe. So now all the parts are together. Are we ready to start your vacuum? All right, so you're going to take your plunger and you're going to slowly pull it down and watch what happens to your marshmallow. As your marshmallow expands, as we're drawing out that air. Now everybody put it back in, let it go. And you've all created marshmallow raisins. So this is your vacuum chamber to take home with you. Do not leave it here in the museum. Go ahead and take that back.
All righty, so that is not the end, my friends.
No, just when you thought we were finished with the vacuum chamber, we're not.
Yes. Oh my God.
So
All
now
right,
we're
we
going to
have
start.
one more demonstration with the vacuum chamber.
Can Miss Carissa get everybody's attention? Everybody, because this is kind of messy. And you don't want to miss it, because once it's a mess, we can't unmess it.
No, we
So
cannot.
is everybody ready? Yeah! All right.
All right, so you saw the balloon. You guys saw the marshmallow. My absolute personal favorite, we've got to do it every single time, is shaving cream. So if a balloon is like one bubble that doesn't or may not pop, and a marshmallow is many bubbles that pop, shaving cream is like a lot of bubbles, because it's a foam, right? So I put a lot in here on purpose.
Oh.
Woo! There we go.
Guess who's cleaning up?
Oh, wait. We have a mat, a slightly protective mat. All right. So, are you guys ready to see what's going to happen to this shaving cream? I think you all have an idea of what's going to happen based on the last two, okay? All right. And here we go. It's getting bigger. It takes its time, but it's going. How big do you guys think it's going to get? Do you think it's going to get this tall? Do you think it's going to get this tall? Do you think it's going to get this tall?
Do you think it's going to push the vacuum lid off?
It does kind of look like ice cream. You're right. Kind of looks like a growing mushroom or something, right?
I don't know. I think we should stop.
I think we should.
No, I think we should stop. No, I think we should. Carissa, I think we should stop.
All right.
I really think we should stop.
Whew. Now, how small do you think it's going to get? Really small. All right, are you ready? It got really messy, right? So kind of similar with the marshmallow raisin, this structure, because it's so much air, pretty much becomes a liquid. So there is a lot of pretty much liquid shaving cream in here. I don't know if you can all see that on the camera, but yeah, it went pretty much everywhere.
It's a mess.
It is. All right, here. Do you want to set that over there?
Of course, now I have the mess.
We'll just sit on the floor or something.
Yeah.
All right, give us 1 second just to get this mess out of the way. Okie dokie. So, you can see from the shaving cream, the marshmallow, the balloon, it's really important for us to protect our astronauts when they're out in space, right? Because what happens to a person when they're out in space? Well, their face would swell a little bit, and also tiny air bubbles would show up in their bloodstream. So that's why they have to wear spacesuits. Those spacesuits keep them safe when they're out doing their spacewalks. And also, speaking of walking around in space and moving, they have to be careful of every move they make because of microgravity. Can you guys say it with us? Microgravity.
Everybody said, good job.
That was really good.
Excellent.
Thank you.
Yeah.
Thank you. So what is microgravity? Well, micro means little, so microgravity means little gravity. So yeah, it's pretty much, that's why in all the videos of astronauts in space, you see them floating around and stuff on the International Space Station, because the effects of gravity are much less on them up there than they are down on Earth. But what happens to the human body because of microgravity? Well, first of all, you actually would get a little taller living in space, because gravity isn't pushing down on your spine. It allows it to stretch out. Also, I mentioned your face in a vacuum. Well, in microgravity, your face would also get puffy. This is, again, because gravity isn't pushing down on the fluids of your face. It just kind of hovers in your face. Also, while you could lift 100 pounds with just your pinky, your muscles would get weaker because they don't have to work as hard to lift that weight. And then also, your heart is a muscle. Your heart would get weaker as well because it doesn't have to push as hard to move your blood around your body. So lots of things happening in microgravity. As a matter of fact, about a decade ago, we did a study. So astronaut Scott Kelly's twin brother, Mark Kelly, stayed on Earth while Scott Kelly was off in space, which is why we named our marshmallows after them. So they spent that year in space to really see, especially because they're twins and they were both astronauts. They're both retired now, but at the time, Mark was already a retired astronaut. You could compare them on a genetic level to see how the body changes after being in space for longer periods of time. So first up, actually, Scott developed eye abnormalities. So he did get vision problems. The structure of his eye changed. Let's see what else. His gut flora changed, but that went back to normal after he was back on Earth. And over 91% of his gene expression, and what gene expression is pretty much just the process that your DNA creates a product, usually protein. So over 91% of it went back to normal in the 6 months after he returned to Earth. But that does mean that about 9% of it didn't go back to normal after 6 months. And it's been a lot longer now, so I'm not sure if that percentage has changed. But at the time, that is what it is.
Well, it can't be all work and no play up in the space station, right?
Astronauts
Carissa?
love to play in space.
So let's see a little bit of play in outer space.
Oh, yes.
Apparently soccer's big. I don't know about you, but I want to spin in space. How many others want to spin in space? Yeah.
He was going so fast.
Yeah,
Yes.
absolutely.
But even though, astronauts love playing in space, they actually have to make sure that they can do everything safely in microgravity. Everything from chores, like getting dressed or doing research, and everything to the eating, even. I mean, eating is difficult in space, first of all, because the gas molecules around the food don't like to drift away, so that it's hard for them to smell it because of that. And also, astronauts get stuffy noses when they live in space, because the fluid reacts differently, so everything just kind of stays up there and it makes it stuffy. So when you have a cold, it's really hard to taste the food that you're eating. It's the same thing because they can't smell it, because if they can't smell it, they can't taste it. So even eating is an ordeal for them.
Yeah. There's lots of other challenges. So we talked about the challenge of getting to space, surviving space in a vacuum, eating, working, playing, and drinking. What else do you think might be a challenge after you've eaten and you had your drink? might be another challenge in space. Brushing your teeth is a good one. Anybody else? What else?
I'm hearing bathroom.
The bathroom, exactly. How in the world do astronauts go to the bathroom? Well, thankfully, we have some clues into that, and so we're going to go and dive deep into it. So the first thing that astronauts have to do is they have to relearn everything about going to the bathroom. Basically, they have to be potty trained all over again, okay? So I've got a space toilet right here. How does it compare to the toilet at your house? The tube. Yeah, well, it does have a seat in it, so that's good. But yes, you can see that there's this hose attached to the toilet. What do you think that hose is used for? What do you think? Yes, exactly. That's where you go, number one. So that hose is actually like a vacuum hose that sucks the urine into a chamber. Now, do not use your vacuum hoses at home like that. That is not necessary. All right, so the other thing about our space toilets is you can see right off on the sides, they've got some handlebars. It's almost like being on a ride. So they're going to turn those handlebars in. That keeps them seated on the seat so they don't float around, right? Because they're floating in space. You don't want to be floating while you're going to the bathroom. So the astronauts actually had to learn about this. And how did they do it? They put a camera inside of the toilet bowl and a television screen in front. So that way they can aim properly to make sure that once they seated center, they create a vacuum. Because unlike space, for us, we have gravity and water to wash all that waste down the drain, right? They don't. So if they don't create that seal, something floating might come up and hit them. And you don't want that. That is an ugly picture. So let's change that viewpoint, okay? Let's think of something beautiful. A beautiful picture from space. When the astronauts on the space shuttle were asked what is the most beautiful, gorgeous picture they saw when looking out into space, do you know what their number one answer was? What do you think? Earth? Anybody else?
Mars,
okay.
The moon.
Yeah, all of those would be absolutely beautiful. But they said it was the urine dump. Yes. So they actually had to dump that chamber before they landed to reduce the weight. So as soon as they released that had the urine dump, how many times can I say urine dump? They actually released it. And as soon as the urine hit the space, it crystallized into this beautiful picture. But we don't have that picture. Sorry, because now they recycle that urine. So instead of dumping it, it is recycled into drinking water. Any of you thirsty? No? Okay, that was kind of gross. But again, there's lots of challenges. And another challenge you may not have thought of is dust. We have space dust. Carissa, can you give us any housekeeping tips on that?
Of course I can. So yes, like Wendy said, space dust is a real problem, and it's kind of made of a lot of the same stuff that it is here on Earth. So you may have heard this before, but dust on Earth is mainly made up of human skin cells, right?
Ugh.
I know, but it's the same thing on space. So that dust is really important, especially because it doesn't go down, again, because of microgravity. It's just in the air, so you really don't want that. You don't want to breathe that in from someone else. So next up, we have a video of space dust.
You might want to shield your eyes.
Yes. And on top of that, it's even worse than usual because their calluses, they're not using their feet like they do on Earth, so their calluses fall off. So all those little specks that you're seeing floating around, that is skin. That is skin off their foot. I know.
Space dust.
Yes, space
dust.
dust. Thank you. It's the
Yeah.
space dust. This is why when they get changed and particularly remove their socks, they stand next to a vacuum vent that sucks all of that space dust out of their air so that they don't have to breathe in each other's skin. It's pretty gross. But yeah, so this is why we actually have to keep studying microgravity, and this is why we continue to study it, so that way we can make sure that we are protecting, like I said before, we're protecting the astronauts up there as much as we possibly can from anything that could happen to them from the long-term effects of microgravity.
Yeah. So that is just about it for our presentation, but I did tell you we were going to do some more rockets, right? So I am going to need 3 volunteers. So Chris, if you could get my 3 volunteers for me.
Alrighty. How about you over there in the red? You on the edge here in the black shirt, and then you at that table with the red. Yep.
All right, so what we have set up for you are some stomp rockets. So we are actually going to use air, and it's the force that you use when you stomp on it to set them off. So if you'll go on to that one, and if you'll come here, and we're going to have you step on this one, and you over here, we're going to have you step on this one. So we need a countdown. All right, 3, 2, 1. Woo! So that was very fun, but you know, Carissa got to do her favorite experiment. I think I should have my favorite experiment, right?
All right. Thank you, volunteers. You guys can head back to your seats.
I have one last thing, and I think you guys should like this one because it's a treat for you. Thank you so much for being here.
Oh, thank you.
But I am going to launch. This is my T-shirt cannon. Now, I don't have a T-shirt. I only have a ball. But when I launch this ball, if you are the lucky winner of the ball, come on up here and we will trade it in for a T-shirt. So I need thrust to shoot my ball out into my audience, right? So inside my launcher, I have some water. And if you will hold this, Carissa,
Absolutely.
for me, I am going to add to the water calcium carbide. Now, if you have been through our Science in Motion, you probably saw some of the headlights for our motorcycle and our cars. They actually used calcium carbide and water in their headlights. And miners also used it in theirs. They would have their headlight on. They would have a water chamber, or they would have the calcium carbide rocks at the bottom. They would have a water chamber at the top that would drip water. And then they would light it. I don't know if I would have that on my head, but we're going to add just a few to our water. Now, when these two combine, they cause a chemical reaction which creates an acetylene gas. So I'm going to dump my, oh, that's a lot.
And I'm going to stand over here.
Let's, this could be loud.
Could.
I think I have enough. So anyway, this is not a very good science of materials here. So I'm going to go ahead and close up my chamber and allow that acetylene gas to build up. And we're going to go ahead and light it. Now, I have no idea where it's going to go. I'm just going to go ahead and light it. Are you ready? Of course, we need a countdown. 3, 2, 1. Uh-oh. I didn't have very much in there. So there we go. Thank you guys so much. Don't forget, we've got everything over the west. If you wanted to sit on a toilet and aim, we've got one out there. If you want to see what it's like to be in microgravity, try our Destiny lab. As it rotates around you, you feel like you're walking without gravity. Thank you so much, and have a great afternoon.